putting this video in the middle of our discussion of buffers. What I'm trying to do is emphasize that a lot of the calculations we're going to be asked to do with buffers and then later on with titrations are really all the same types of calculations, and they just involve acid-base reactions. And so I hope that if you approach these problems as just treating buffer problems and titration problems as just reactions of acids and bases, maybe that'll make it a little bit easier and a little bit easier to sort of see the connections and see how the problems are very similar. So when we mix an acid and a base that aren't conjugates of one another, if they're conjugates, they're going to make a buffer. If they're not conjugates, the acid and base are going to react with one another, and they're going to neutralize each other, and so one of them, whichever one is the limiting reagent, runs out. And so for these acid-base reactions, one of the difficult things is just writing the chemical reaction that we're interested in. And so the first couple examples we're going to look at are just examples of writing these acid-base reactions. So in our first example here, we have the reaction between hydrobromic acid and potassium hydroxide. And hydrobromic acid is a strong acid, and potassium hydroxide is one of our strong bases. So we could write the reaction using the reactants HBr and KOH, but I'm actually going to encourage us not to do that. Right? We know that HBr is a strong acid, and so it's going to completely ionize in solution. And so whatever HBr we started with, that's going to be converted into bromide ions and hydronium ions. Right? So the thing that we really have that's going to be reacting with the base is not HBr, but it's really the H3O plus that the HBr partially becomes when it ionizes. So the reaction that I would write for this, rather than using HBr, since that's a strong acid, I would use H3O plus. And then for the potassium hydroxide, the KOH, again, that's an ionic compound that's soluble in water. It's going to completely dissociate, so we're going to have K plus ions and OH minus ions. Well, the K plus ions aren't going to be doing anything. What I'm really interested in with these strong bases is the hydroxide. So the reaction that I'm really interested in when HBr reacts with potassium hydroxide is this reaction. Sure, I'll put in my states there. So this isn't true for weak acids and bases, but when you have a strong acid, right, we want to think of what we really have in solution as H3O plus. And when we have a strong base, what we really have in solution is hydroxide ions. So the reaction between hydrobromic acid and KOH, I think, is best represented by this chemical equation. Okay, here's another example. We just want to write the chemical equation for what's going on here. So in the last example, when we had a strong acid, we wrote it as H3O plus because it's going to completely dissociate. In this case, we have acetic acid, which is a weak acid. It doesn't completely dissociate, so I'm not going to write it as being equivalent to H3O plus. So in this case, since I have a weak acid, I will take and write it as that. Now I have a strong base, the sodium hydroxide, so that, just like the KOH in the last example, is going to completely dissociate. So what I'm really interested in the case of a strong base, is the hydroxide ions. And so then the products of this reaction will be this. And if you notice, both in the last example and in this example, when I have an acid reacting with a base, I don't use equilibrium arrows because this reaction is going to go to completion until one or the other runs out. Okay, here's another example. Now I have a strong acid and a weak base. And so HNO3, that's one of our strong acids. So instead of writing HNO3, just like with the HBr in the first example, I think it makes sense to write that as H3O plus. And now ammonia is a weak base, so I won't replace that with hydroxide. I'll use the formula of my weak base. Right, so the H3O plus is going to donate a proton to the ammonia. And so that's going to give me water. and ammonium ions. All right, so we've just practiced writing reactions between acids and bases. And now what we want to do is calculate the pH after the reaction happens. And so this generally involves two steps. So the first is a stoichiometry problem. And we've essentially been setting up the equations that we're going to use for those stoichiometry problems in these previous couple of examples. Right? The acid and base are going to react with each other. And we're going to make a table to help us determine the lim reagent and finding out what is present at the end. We'll do an example of that next. But I want to point out this is not an ice table. Right? The first step in these acid-base reactions is a stoichiometry problem. It's going to go to completion. So we don't use an ice table. It's going to look very similar, but I want to be clear that we should label it differently because we're not dealing with an equilibrium problem. We're dealing with a reaction that goes to completion in the first step. All right, so once you've done your BCA table that we'll do an example of next, we want to look and see what's present at the end of the reaction. And that will determine what we do with the second step. And so after we do the stoichiometry problem, depending on what's left, we very likely will have an equilibrium problem. And so we'll take what's left, and it's either going to be an ice table, or if we have a buffer, if we have both a conjugate, a weak acid and its conjugate base, or vice versa. If we have a buffer, we can use the Henderson-Hasselbalch equation. Now, if we have any hydronium ion or hydroxide ion left over, if we have any strong base or acid present at the end of the reaction, then we don't actually have to do an equilibrium problem, right? If we know the H3O plus or we know how much OH minus we have, then we can calculate the pH on that. Now, one last thing I want to say before we do some examples. When you do the stoichiometry problem, when you do the first part, because we're doing stoichiometry, we need to work in moles. If we have a situation where we need to do an equilibrium problem, make sure you're working in molarity. When we do equilibrium problems, we always have to be working in molarity units. Okay, so here's our first example. We want to know what is the final pH when 25 milliliters of 0.1 molar hydrochloric acid is added to 15 milliliters, and there's a typo here, of 0.2 molar sodium hydroxide. So I recognize this is an acid-base reaction because I have a strong acid reacting with a strong base. So the first thing I want to do is write down the chemical equation. And since I have a strong acid, instead of writing HCl, I'm going to write H3O plus. And since I have a strong base, sodium hydroxide, instead of writing NaOH, I'm going to write that as OH minus. And so then this reaction is going to go to completion, and that's going to make 2 moles of water. Alright, now when I have these acid-base reactions, they go to completion, and my first step is to do a stoichiometry problem. And so I need to work in moles. So this is where I have, right with my BCA table, I'm going to have the moles before they react, the change in moles as a result of the reaction, and then how many moles I have at the end of the reaction, or after the reaction has completed. And so I need to know the moles of HCl, right? So I'm going to use that molarity is equal to the moles over the volume, or the moles is equal to the molarity times the volume. So for HCl, or what I'm writing as H3O plus, I need to use that I have 0.100 moles per liter times, and then the 25 milliliters I need to be in liters, so I have 0.025 liters. So that's going to give me 0. So that's the moles of HCl, or H3O plus. All right, we'll do the same thing for the hydroxide. So now my concentration is 2 molar, or sorry, 0.2 molar, or 0.2 moles per liter. My volume is 15 milliliters, so that's going to be 0.0150 liters. And so I get 0.003 moles of hydroxide. Alright, so to finish off my BCA table, I'm not really worried about the water. I can include it here, but that's not going to affect the pH. And so I look at the hydronium ions and the hydroxide ions, and since this is a one-to-one reaction, whichever one of these is the smallest, that is going to be the limiting reagent. And so I have less moles of hydronium ions, so they're going to run out first, and so that's going to determine what the change is for both the reactants. And so I'll be left with no hydronium ions and 0.0005, or 5 times 10 to the minus 4 moles of hydroxide ions. So at this point, if I had no strong acid or strong base left, I might need to do an equilibrium problem, but that's not the case. All I have is leftover strong base, and I know how many moles I have of the hydroxide, and I know what the final volume of the solution is going to be. So if I can calculate the concentration of hydroxide ions, then I know that I can get the pH from that. So let's finish this up on the next slide, just so we have enough room. Alright, so we determined that we had 0.0005 moles of hydroxide ions left over at the end of that reaction. And so to get the concentration, or the molarity of the hydroxide, I need to divide the moles by the total volume. So the moles is what we calculated from our BCA table. Right, our total volume, 25 milliliters plus 15 milliliters, I have 40 milliliters, but of course I need that to be in liters, so 40 milliliters is going to be 0.04 liters, and so for my concentration of hydroxide, I get 0.0125 molar. And once I know the concentration of hydroxide, it's easy to find the pH. So there are a couple ways we could do it. I like to go the pOH route. So the pOH is going to be the negative log of the hydroxide ion concentration. So for the pOH, I get 1.90. And then we know that pH plus pOH has to be equal to 14. So the pH is going to be 14 minus 1.90. And so for my final pH, I get 12.10. Okay, here's another example to finish off the video. So in this case, I'm again mixing two compounds, and I have a strong base and a weak acid, so this is going to be an acid-base reaction. So the first thing I want to do, before we write out the numbers, let's go ahead and write down the chemical reaction that we're interested in. So KOH is a strong base, and so instead of writing KOH, I'm going to write OH minus. Now HNO2, nitrous acid, is a weak acid, so I can't replace that with H3O+. So I am going to write HNO2. Now these acid-base reactions are going to go to completion. And so when that acid donates a proton to the hydroxide, that's going to give me water and NO2 minus. Alright, now, whenever we have these acid-base reactions, we always start with a stoichiometry problem. So I need moles. And so I'm going to have my BCA table, and I need moles. I need the moles of the hydroxide ions and the nitrous acid. So let's start with hydroxide. Right, again, the moles is going to be the molarity times the volume. And so the molarity of hydroxide is the molarity of potassium hydroxide, so that's 1 mole per liter. I have 100 milliliters, but that needs to be in liters. So that's 0.1 liters. And so I have 0.1 moles of hydroxide. So we'll go ahead and put that into our BCA table. Now we need the moles of nitrous acid. We'll find that the same way. One molar, or 1 mole per liter. Now we have 150 milliliters, so that would be 0.15 liters. Okay, so we can go ahead and put that in. Initially, we don't have any nitrite ions. The water's not going to affect the pH, and so I'm not going to worry about it. And then for these BCA tables, when I'm doing stoichiometry, we can determine the limiting reagent. Right, this reaction is going to go to completion, not to equilibrium. So whichever one I have less of is going to be my limiting reagent, in this case the hydroxide. And so that's going to determine how much everything changes. So when we lose 0.1 moles of hydroxide, that will neutralize 0.1 moles of nitrite, of nitrous acid, and that will make 0.1 moles of the nitrite ion. So when this reaction finishes, I'll have used up all my hydroxide, but then I'll have 0.05 moles of nitrous acid and 0.1 moles of its conjugate base. Right, so now this is where we have to decide how we're going to finish this problem. So if I'd had any hydroxide left, whenever you have either strong base or a strong acid left over, that's all we need to do to find the pH. And we'll never have both hydroxide and hydronium ions present at the end of the reaction. If that ever happens, something has gone wrong. But in this case, I don't have any hydroxide. Right? But what I do have is a weak acid and its conjugate base. And so this is a situation where what we have left in solution is a buffer. And we know how to calculate the pH of a buffer, and the easy way to do that is using the Henderson-Hasselbalch equation. So we can use that pH is the pKa of the acid plus the log of the concentration of the base over the concentration of the acid. And so just because I'm out of room, I know there's not much left, but let's go ahead and finish this off on the next slide. Okay, so to finish up this problem, we need to know the pKa of the acid. We were given the Ka, so I just need to take the negative log of that to find the pKa. And then in principle, when we use the Henderson-Hasselbalch equation, what we have here is the concentration of the base and the concentration of the acid. Remember, in these BCA tables, all of this is in moles. And so, in principle, we should have to convert our moles back into, divided by the total volume to get the concentration. But the base and the acid are in the same mixture. And so the total volume is going to be the same. So when I divide the moles of the conjugate base by the total volume, 150 milliliters or 0.15 or 0.25 liters, 250 milliliters, right? I'm going to divide both the moles of the base and the moles of the acid by that same concentration. So they're just going to cancel out. So in this case, it's okay to use the moles because the total volume is the same, and so the volume is just going to cancel out in the calculation. So remember, when you're using Henderson-Hasselbalch equation, we formally have to use molarity. If you're ever not sure, go ahead and convert it into molarity. But if you recognize that the volumes here are just going to cancel out, then it's okay to go ahead and use moles and save ourselves some time. So pKa of the acid is the negative log of the Ka. So we have the negative log of 4.6 times 10 to the minus 4. And so I'm getting 3.33. And so then to finish the pH, it's going to be the pKa plus the log of the base is the nitrite ion, the acid is the nitrous acid, and I get a pH of 3.63.